In this tutorial, we are going to perform a optimization of an arbitrary beam cross-section with MSC Nastran. My name is Christian Aparicio, and I'll be going over today's tutorial. Now, this is what we want to do. I'll show you in a moment how to create this arbitrary beam cross-section on the left. We are going to use the optimizer in MSC Nastran to adjust the width and the height of this beam cross-section. So by the end of this tutorial, we should expect a difference in optimized height and the width for this arbitrary beam cross-section. Now, let's go ahead and jump out of here and show you how to go ahead and start about this. So step number one, the user's guide has a starting bulk data file. So let's go ahead and open that bulk data file. Let me go ahead and import this bulk data file to the beams viewer that's available in the SOL 200 web app. We want to look at what the finite element model looks like that's contained in the bulk data file. So here is the beams viewer. Let's go ahead and navigate to that bulk data file and let's import it. So here we see a few line elements. We see the line elements are using this so-called T cross-section, but in a moment, I'm going to show you how to construct this cross-section that you see on the left-hand side of the screen. So to define an arbitrary beam cross-section, we are going to open up what's called the PBMSECT web app. So let's go ahead and open that up. And let's go ahead and import that bulk data file. Now that I've uploaded this bulk data file, we are going to have a chance to add additional bulk data entries. What I want to use this web app for, I want to define a PBMSECT entry and add it to this bulk data file. So here, this is what we're going to do. We're going to click Create New Entry, and we're going to adjust the configuration of the cross-section. I want to use PBMSECT 1. I want to use PIDU 1. I want to use the existing MAD1 entry that's in the cross-section. And I want to use a close profile for this cross-section. Now let's go ahead and create some points. But before I go ahead and create some points, let's adjust the width and height of this mesh and then the number of divisions in the mesh or the grid. Let me click Fit Model here on the center of the screen, and now we have this zoom in version. Point 1 is going to be the width and the height of this grid. Point 1 has units of length. Whatever your units of length are for the bulk data file, this is the same units for the width and height here. Now let's go ahead and create a few points for this cross section. Let's go ahead. Now, you don't have to get exactly the same points in the same spot, but you want to generally have the same number of points. So let's go ahead and create a few points that you see here on the screen. Now, I'm going to diverge a little from the tutorial file. Here, the reason I'm doing this, I want to show you that it's okay to diverge a little from this tutorial. So here, I've created these, what looks like 9 points. Let me go ahead and click Create Lines. Let me go ahead and create these few lines. This is the process of connecting the points. And let me just go ahead and repeat the process here and here. And let me go back here. Now, I think I might have to take a step back in a moment to redo this, but here, okay. Now, I've clicked cross-section preview, and you see that things don't look right so far. That's because the thickness is really large. So let's go ahead and minimize the thickness a little. And now this looks a little bit more reasonable. Let me go ahead and now click Select Lines of Outer Perimeter. And let me go ahead and make sure that all of these outer lines of the cross-section are out P lines. So here, these 9 lines for the type column are set as out P. Let me go to Run MSC Nastran. Here I have the equivalent entries for this arbitrary beam cross-section. Let me click Run MSC Nastran. It's always important to look at what MSC Nastran thinks the arbitrary beam cross-section looks like. So here, let me visually inspect. Things look good. Maybe I want to do a few more adjustments. If I look at the tutorial file, and the tutorial file is available in the user's guide. If you click at the right-hand column, this is a PDF file. You can follow along with this tutorial. If I look back at my tutorial file, which would be this file, if I navigate to the section that tells me how thick the line should be, I see I should be using 0.01, which I'm using here. So far so good. And now let me create a few additional lines. So if we look back here, and so let me go back to create points. Let me create points here. And let me create these additional points. And let me create these lines. Now, here again, I'm diverging from my own tutorial. This line, for example, this line should be perfectly vertical, but since I'm going off script a little, there's a slight angle to this line, which is perfectly fine for this tutorial. Always make sure that you've properly defined your out P or outer perimeter line. So here, since this is a closed profile section, the outer perimeter lines, the blue line, should be connected at the ends and continuous. But here you can see that this is where the outer perimeter ends and this is where the outer perimeter starts. There's a gap. So this is not okay. So here I clicked on select lines of outer perimeter. Let me go ahead and select these few lines, and now the outer perimeter is continuous. Let me go ahead and finish this. I think I forgot to create a 1 point. So here, let's go ahead and finish or create that additional point. And let me connect this line. I suspect that I've created a configuration that's outdated. So again, let's go ahead and select the blue outer perimeter line. So things look okay so far. Let me turn on a preview. What does this look like? So the blue again are the outer perimeter lines, and every other color is a different type of line. So here we see that we have a branch 1 set of lines and a branch 2 set of lines. So let me look at here, and let's go ahead and try and run MSC Nastran. We want to make sure that this set of bulk data entries runs fine with MSC Nastran. And now let me look at this. Okay, things look good so far. One thing that we might want to do, let me look at this. And if you notice here in a moment, let me zoom in. Let me just copy these bulk data lines, actually. And let me zoom in. So far, if we look at the PBMSECT entry, we have one thickness keyword. If we wanted to optimize this arbitrary beam cross-section, we can at most only change one thickness since there's only one thickness keyword. So you might be wondering, hey, I want to actually optimize the thickness of some of these lines. How do I do that? How do I get distinct different thickness keywords in this entry? This is how you do that. So let me turn on the labels. I'm going to turn off the preview. Maybe for lines 11, 1, and 2, you want to have a different thickness. So let me go ahead and show you how to do that. So 0.010. Here I'm typing the equivalent thickness of 0.01, but I'm adding an extra 0. The reason the extra 0 is done, let me go ahead and create a new file here and show you that to the right. I get a second thickness keyword that's equal to that distinct value, 0.01, with the extra 0 at the end. Now, if I wanted to perform an optimization, I have the opportunity to vary or optimize this in different thickness value. So let me go ahead and repeat the process. for these additional lines. So here are lines, maybe, let me actually look at my notes and see what we're trying to do here. So lines 1, 2, and 3. Let's see. 1, 2, and 3. Okay, now I know what we're doing. Let me take a step back. This point here is not supposed to be here. So let's go ahead and click remove points. And when we remove the point, the adjacent lines are removed. But that's okay. Let me go ahead and create a line to make up for that missing line. Let me make sure that my line, my outer perimeter lines are continuous. Now let me go back to the labels, and this is what I want to do. For lines 1, 2, and 3, I want to have a distinct thickness value. Now here, the thickness is the same. We turn on the thickness is the same, but the inclusion or the addition of an extra 0 makes this algorithm generate this extra thickness keyword. So now in a moment, when I perform the optimization, I'm going to perform a thickness optimization for this separate thickness. So here, let me go ahead and look at what we have left. Let me look at my notes just to make sure things look good so far. So here, I'm going to use a default thickness of 0.01 and then a thickness of 0.010. Let me run Nastran, of course, to make sure things look okay. And so far, so good. Let me look at or rather the rest of the tutorial to make sure things look okay. Okay, perfect. Let me go to the very bottom and let me click download. This zip file contains the same bulk data file, but it has a few differences. So here on the left is the original bulk data file. Here on the right is the new updated bulk data file. If you look at the section immediately after begin bulk, we now have the respective PBMSECT entries that correspond to this arbitrary beam cross-section. So those are included now. But now we have to make one adjustment. You see this PBMSECT 1? It's going to conflict with this existing PBML1 entries here. So let's go ahead and move or change the ID of this entry. Let's change it from 1 to 9 maybe. If we look at these PB entries, if we look at the second column, we see that these line entries are referencing a property with the ID of 1. If we look back at this PBMSECT entry here, this is PBMSECT 1. So now these C-beam entries are pointing to this PBMSECT 1. Now, as always, let's go ahead and run Nastran to make sure that this new updated bulk data file runs properly. We don't want to have any issues so far. So let's go ahead and open up the F06 file. And let's go ahead and look for any fatal messages. So we'll look for fatal. And things look good so far. Let's actually make sure we get some results here. And I think the file is outdated. So let's go ahead and redo the search. Things look good. So far there are no fatal messages. Looks like we actually get some responses like forces in the beam elements. So this bulk data file on the right is running okay so far. So now we're done constructing our arbitrary beam cross-section. Let's go ahead and open up the beams viewer and let's go ahead and upload this updated bulk data file. Let's go ahead and look at that. And in a moment, we're going to see what the beam elements look like with this updated bulk or arbitrary beam cross-section. So this is what we have so far. Perfect. Now this is what we want to do. We want to optimize the width and the height of this arbitrary beam cross-section. So let me go back here. So this is what I want to do. I want to optimize the point-to-point width of this cross-section, and I want to optimize the point-to-point height of this cross-section. Also, let me show you what we want to do for the thickness. So maybe I'll make this a little beefier just so you look at what's going on here. Here, I want to vary the default thickness of all these other lines. So line 11, 10, 9, 15, 8, 7, 6, and so on and so on. I want to vary the thickness of those walls or lines, if you will. Separately, I want to vary the thickness of these three lines, lines 1, 2, and 3. So remember, in the bulk data file, the PBMSECT entry has two distinct thickness keywords, or T keywords. So we're going to vary these thicknesses. So let's go ahead and jump back to the SOL 200 web app. I've already opened the size web app. So let me go ahead and make a few comments about the problem statement. So a moment ago, I just mentioned that we want to vary the width and the height of the arbitrary beam cross-section, and I want to vary the thickness of these different lines. We want to minimize the weight of this entire set of beam elements, and I want to make sure that the displacement at this node is between negative 0.01 and positive 0.01. Let me look here. One thing I should mention here, for the width, height, and the thickness, we are going to have different bounds, if you will. So let's go ahead and jump out of this. Let me go back to the size web app. Let me go ahead and select that updated bulk data file that contains the PBMSECT entry, and let me upload it to the SOL 200 web app. Now, the SOL 200 web app has gone ahead and defined all the different properties, materials, and even the elements, the C-beam elements that could be set as design variables. But here, I want to set the width, the height, and the thickness as 4 separate design variables. So let's go ahead and jump here to this next table where we can adjust my bounds. So the lower bound will be 0.08 for the width, 0.05 for the height, and for the first thickness, we're going to prevent the lower bound, or rather prevent the thickness from going less than normal, 0.002. Going to repeat this for the next thickness. Let's see, the upper bounds, 0.2, 0.02, and 0.02. Okay, here on the right-hand side, we have the respective dV per L1 and the des of our entries. Things look good so far. Right, okay. Now, let's go ahead and jump to creating the objective. So we're going to go here, and we want to set the weight. We want to minimize the weight. Let's go ahead and create our constraint. So remember, we want to generate a constraint on the deformed shape of these beams, if you will. So this beam, let me turn off the beam shape. Let me turn on the grid labels. And let me resize the labels, if you will. So maybe they're too big. Let me zoom out a little. So this point here, let me zoom in a little. It's kind of hard to see here, but if I change the background color, maybe that will help a little. This point, this grid is going to refer to point 6 or grid 6. So let me go ahead and shrink that a little. Let me change the color. Right, so this is going to be grid 6. We want to make sure that the deformation is no greater than these bounds. So negative 0.01 and positive 0.01. The grid ID should be 6 and the component should be Z. So positive Z. Let me jump back here. So the third component, if you will. Let me go ahead and make sure everything looks okay here. So we have the variables, the objective or the DRESP1, and the DRESP1 and the deconstraint entry. So now let's go to the exporter and download these bulk data files. In a moment, we're going to go ahead and get a new zip file. And one thing to keep in mind, sometimes Nastran doesn't like special characters like parentheses or blanks in the directory name. So we're going to remove the blanks and the parentheses symbols, and we're going to just use _1. Let's go ahead and start MSC Nastran. This will go ahead and start the optimization process. Remember, right now we're going to have the optimizer vary the width, height, and the thicknesses of the walls of the arbitrary beam cross-section. So here, I think the optimization is complete. So in a moment, we should see changes. Okay, so this is what we see. The objective started with a mass of 37 units of mass, and at the end we get a new cross-section with a mass of 5.63. Let's look at maybe the height or the width of the cross-section. We started with the width of 0.1, and we ended off with the new width of 0.08. And in here for the height, so the height is going to be the orange line. We started off with the height of 0.1, and we ended off with the height of 0.05. What about our thicknesses? Let's look at what that looks like. So both thicknesses started with an equal value of 0.01. But now for one of the thicknesses, we have a value of 0.003. And for the other thickness, we have a value of 0.002. Now, here we might have a question. What does the actual cross-section look like now? If we go back to the directory where we have performed the optimization, we get a new directory called workspace B. Inside of this directory is a new bulk data file, but this new bulk data file has the same PBMSECT entry, but these entries have been updated to be the optimized cross-section, if you will. If we look at this file on the left, this is the starting cross-section that we built in the PBMSECT web app. So this would be these entries here. Here on the right, this is the bulk data file in workspace B. These bulk data entries are the optimized bulk data entries with the optimized width, height, and the thicknesses for the walls. What we can do with this new file, we can go back here to the beams viewer. Let me go ahead and open up a new window. And for consistency, let me go ahead and turn off some things here. And let me fit the model. Let me go ahead and upload that bulk data file found in workspace B. And we are now going to have an opportunity to look at what the new arbitrary beam cross-section looks like. So if we look at this is what we see. We see one big difference right now. Let me go ahead and actually adjust this original model so we see what's the difference now. We see one thing. Number one, the height of the cross-section is a lot shorter now. So that's what you can see here. The thickness values, let me look at the thicknesses. I think the final thickness values are very close to each other, 0.003 and 0.002. So here, it's kind of hard to see that the thickness of these three walls was minimized, or that they're actually different. What might help here, let me go ahead and open a new PBMSECT tool. Let me upload the updated bulk data file. This file is again the file that contains the optimized cross-section. And here, let me turn on the labels. Here you can see what the height and the width is. If I turn on the preview, and if we go to these line segments, we can see that the default thickness is now the optimized value of 0.002, and the thicknesses for these three lines is 0.003. So you could use all these different tools. You could use the XY plots here, the variables. You could use the beams viewer, or you can use the original PBMSECT web app to look at what your optimized cross-section looks like. So let me look at my notes to see if there's anything more to do for this tutorial. Nope, things look pretty good so far. Maybe one thing I'll leave you off with, just in case you have any questions or comments, you're always welcome to contact me at the email address that you see here at the bottom side of the screen. So with that, I'll end here. Thank you so much for watching.